Hopefully they show
I call your name, come pick up your quiz. Tyler, Clay, Kelvin, Tony.
Pardon the interruption, at this time, our code yellow is listed for all buttons, schedule
There's a school shooting, but it's okay. I had a paintball gun.
Ed, Mackenzie, Seth, Vinny, Kyle.
This is a lot.
Michael, Patrick, Seth,
Give me mine. Give me mine.
Emmy, Brittany,
What's the scale on the
Cameron. Alright, Jamie, now take a quiz. Okay.
Spicy.
So here is how the scoring worked on this. So there were 3 total standards, so you could have gotten out of 3 on each of those standards. Standard 1 had 3 questions, so questions I think 1, 4, and 5 were standard 1. So the way that it was graded was if you got all 3 of those problems right, I'm pretty much on all these problems just looking for right or wrong. If you got it right on each one of those, you got the full 3 points. If you missed or made a mistake on one of them, you got a 2. If you missed on 2 of them, you got a 1. And obviously, if you missed all 3 of them, then you got a 0. And so question 2 was standard, was for standard 6.2, and then question 3 was obviously standard 6.3. So a little bit of discretion on those, but we'll talk about how the points shook out for that. Overall, pretty good on the quizzes. I was very happy that most people got question 1 correct, that you were able to actually calculate the momentum to a reasonable value on them. So that being said, suppose that you caught a pitched baseball barehanded. The ball has a mass of 0.145 kilograms and a velocity of 35.7 meters per second to the right. As I read that in terms of direction. If the force of your hand acts on the ball for 0.020 seconds, and what is the force, magnitude, and direction acting between the bare hand and the ball? So what did we get for this, Kyle?
I had 259 newtons.
Okay, 259 newtons. Does that sound about right, everybody? Yes. Okay, approximately 259. So if you had like 258.8 something or 260 around there, I went ahead and gave it to you just a minute. Okay, rounded. Okay, this is just a straight calculation, right? It's a straight calculation of changing momentum. So we have an initial momentum, which is just equal to mass times the initial velocity. We have a final momentum, which is what? What's the final momentum of this object? Any idea?
0.
How do you know it's 0?
Because it doesn't move.
It doesn't move, right? The ball is caught in the glove, or well, caught by the hand.
There's no move.
And so its final velocity ends up being equal to 0. Okay, so what that means is that the impulse applied is just going to be equal to the opposite direction of the initial momentum. Okay, and so we know that if delta P is equal to the impulse, delta P in this case is just going to be Pi, F delta T. If we have a time, then we should be able to calculate a force, but just by saying delta P divided by delta T. Okay, so from that we got our 259, 260 newtons. Okay, so the second question, so consider the ball as a system, and you represent the act of catching it using the bar chart. So what I wanted you to do was to draw the bar chart, both with the momentum and impulse. So momentum being first, the impulse applied to it next, and then the total final momentum at the end of it on the other side of the equal sign. Okay, so if we look at the structure on this, what should we end up seeing as our final bar, Brittany? What should our final bar look like?
I put 0.
Why would it be 0?
Because the momentum cancel out.
The momentum cancels because of the impulse, right? That the impulse applied to it, basically the momentums cancel out. Okay, so depending upon how you drew it, you could have drawn it a couple of different ways. Basically, what you had to have was a bar, 2 bars on the left-hand side, one that was above the x-axis, one that was below the x-axis, that were approximately the same size, and then a 0 bar off to the right. So for some people, they had a large momentum bar and a smaller impulse bar beneath that, and then they ended up with 0. So depending upon what you understood, I went ahead and gave you some or all of those points. Okay, flipping over to 3. How would the force be different when a glove is worn and the impulse acts for 0.040 seconds, so doubling the time? Tyler, how would it change?
For number 3, right?
Yeah, number 3. Yeah.
I said the force would be different because the glove would cushion the ball velocity and would be less painful for the person.
Okay, that's one way to put it. Essentially that there's less force because even though the momentum of the ball is still the same, the change in momentum is the same. A smaller force because of a larger amount of time. If we look at the amount of time, what's the difference between this time and the time from part 1, or from question 1? It's double, right? So if it's double, what does that mean about the overall force? It has to be half, right? So if it's 259, 260, then it's going to be approximately 129 newtons or 130 newtons on the other side of that. Okay? So if you made the statement that it would be half of the force, or we did an actual calculation for it, I'm going to give you points. If you just said that the force would be less, if I felt like I gave you a little bit of discretion on that because I do want you to realize that it would be less force, but in the future, if it's something like a number, then go ahead and make a calculation, right? If it just says if the time was longer, what would happen to the force, then you can be more descriptive. But if it gives you a number that you can do a calculation with, go ahead and do that calculation and show exactly what it is. Because in this case, it was supposed to be that it was exactly half. Okay, moving on to the last 2 questions. Again, both of those are 6.1. 2 empty streetcars collide by accident in a rail yard. Runaway car A of mass 21,500 kilograms moving to the right with that speed collides with car B, which is stationary, and 20,900 kilograms, which is at rest. Calculate the velocity of the 2 cars immediately after the collision. So they collide together, they stick, and then they move as one. So what do we get as our final speed, Seth?
Final speed.
11.62 meters per second, and obviously, is it moving left or right? To the right. It's moving to the right. So A slams into B, they both move together. Notice that the speed, is it exactly half, more than half, or less than half of the original speed? How does it compare to the original speed? When we look at the final speed compared to the initial speed of car A.
Less than half.
It's less than half, okay? So in the case of baseball being caught by the hand, we saw that the force was exactly half because the time was doubled. Here, we see that the overall momentum of car B is 0. Car A obviously has some large value. So we know that momentum is conserved. But because of the mass difference, because car B has more mass, it's going to result in a smaller overall speed. Imagine for a second if car B was not, say, 22,900 kilograms. Imagine it was like 22 million kilograms. If car A runs into it, will they move together? Will they move at some kind of a speed?
Yes.
Yes, conservation momentum says they would. Will it be a large speed?
No.
No, it will be an incredibly tiny speed, but it will move, again, assuming no friction. Okay, and then finally question 5, an identical pair of streetcars, each of mass 23,000 kilograms, are coupled in a similar event, except that car A is moving to the right at 3 meters per second, and B is moving to the left at 2.3 meters per second. Calculate the velocity of the system after the collision. Again, it's conservation of momentum. The initial momentum is going to be the momentum of car A plus B, and then the final momentum will be car A plus car B. So once they're stuck together, total momentum will be conserved. So what will be the final speed of the two cars stuck together? Patrick.
0.35 meters per second.
0.35 meters per second, right. So we know that because they are identical in mass, but the speeds are different, whichever car is moving faster, they're going to continue that movement in that car's direction. Okay, so if they had, let's say for example they had collided at the same speed. Let's say they've both been traveling at 3 meters per second. They run together, what happens?
They stop.
They stop. Why?
Momentum conservation was 0 and is 0.
Conservation of momentum. Okay, so one car would have a certain amount of momentum, the other car would have an identical amount of momentum, but different in sign. So when we add them together, again, considering that momentum is a vector, we add it vectorially, it comes to zero. So they just sort of stop. It would be a perfectly inelastic collision at that point. If it was in any way elastic, for example, if you put a spring on one end, then they would just sort of bounce off of one another, and their momentum would still be conserved. That's the other thing too. Momentum is always conserved. Even if something like energy isn't, or you lose heat or something like that, overall momentum in a system is going to be conserved, unless there's some sort of an external force. Okay, questions or anything else that anybody wants to add? Okay, so go ahead and bring those back up and just set them on that pile right there.
I'll grab yours.
So